Are we started?
Yeah.
I'm going to do a quick outline and work in particular one problem, and then I'll be happy to answer questions. So it's pretty simple here. There are really just 3 chapters that we're concerned with since the last one. So we have chapter 7, point estimation. But of course, we quickly realized that that by itself wasn't adequate, and we needed to use confidence intervals. And then we realized even those weren't everything we could do, and we did hypothesis testing. And the hypothesis tests that'll be on the exam are all single sample, single population kind of tests. Later, next chapter, of course, we're already into the 2 population, 2 sample stuff, but that will not be on the exam. It's only on things through chapter 9. Yes, John? ROC. We are not covering ROC this year. I'm sorry, I guess I'm not hearing. OC? Got it. Got it. They say OC. Some people say ROC, receiver operating characteristic. So this is relating the beta and the sample size and that stuff. Not covering it. The only betas we did are the stuff where you guys calculate the betas and the ends using, specific formulas. You don't have to learn how to use those tables. Okay. I will say, if you're interested in medicine, and in particular things like mammography, cancer screening, that kind of stuff, that stuff's used all the time. So you will want to pay attention to it. But for the rest of you, you can defer that for future use. Okay, so let me begin. I've had requests to talk about point estimation and the methods we looked at there. And so they include, so this is chapter 7, method of moments and maximum likelihood. So I want to go through and do problem 7-40, which is one a lot of people were confused by, and I think it does a nice job. Well, we'll use that as a review, and it'll do a nice job of reviewing the key points and then the complications that that problem was supposed to bring out. And I think it was so complicated it confused a lot of people. So, problem 7-40. And we've got a probability density function that looks like C times 1 plus theta. Oops, 1 plus theta times x. And it's defined on the interval from -1 to 1. And you're asked to, in part A, find the value of the constant c, which is real straightforward. We all know how to do that by now. You take the integral, set it equal to 1, solve for c, and you get that c is 1/2. So we'll just take that. Part B, what's the moment estimator for theta hat? Okay, so, one sec here, let me bring it up. Okay, so moment estimators. The idea behind all of these estimators is I've got some property of a probability distribution, and I want to give my best guess for what that value might be. And there are a lot of different ways to do this. We studied these 2 techniques here, the method of moments and the maximum likelihood method. The method of moments says I've got some property of my probability distribution, and I take those moments, and by moments we really mean powers. So we have the expected value of our x, our probability x raised to the k power. And we set that equal to a property of our sample. In this case, it's the sample moment. And the sample moment in this case is just like taking the expected value. You sum up the values from I equals 1 to n of x sub I to the k with a 1 over n out in front to normalize it. So to draw this picture again, here's my population. It has various properties theta. I take a sample, and I have my set of x sub i's. And based on this, I want to go back and estimate my theta hats. And it happens that if I take these moments, I take my probability density function, calculate the expected value to these exponents, these powers, equate them, then I can pop out an expression that includes the theta on this side, and it includes the theta on this side, and it includes things I can calculate from my sample on this side. And when I solve them for the theta, then it gives me an estimate in terms of the samples. Okay, so in this case, there's only one parameter here. So if there's only one parameter, I can hope that I can just use k equals 1. I don't have to worry about any higher powers. Okay. So what's the expected value then of x to the 1? That's just the expected value of my distribution. How do I find the expected value for a distribution? It's already forgotten. It was on the test the first time, so you don't have to remember it anymore. So you try.
Integral of x times x dx.
Exactly. Okay. Integral x f of x dx. And the limits would be minus infinity to infinity, except we know that we're only defined for minus 1 to 1. Okay? So I plug that in. I can grind through the integral, and I get that it's just theta over 3 in this case. Okay, then I set that equal to 1 over n sum of x. And what is this equal to? Sample mean, x bar. So that's easy. And so at the end of the day, my estimator theta hat is just equal to 3 times x bar. Okay. Yes?
When you set those two sides equal to each other, you get theta over 3 equals x bar. So how do you make that transition from that equation to theta hat?
Okay. What I've done here is I've set the two sides equal. Okay. This side has theta in it because theta is built into my population. It's built into my probability density function. Okay. So it just pops out as theta. On the other side, I've got my sample data. I set them equal, and then sort of the setting them equal is what gives me the estimator. So this is just a calculation I do on the population properties. This is a calculation I do on samples, but when I flip it around and I say, actually, I'm going to use the sample properties to calculate, then I put the hat on it. And putting the hat on it says, I'm going to use this to estimate. Okay. So does that answer your question?
So would it be correct to say that the top equation is kind of the process, whereas the second one is...
I'm sorry, I'm having trouble hearing.
So is the second one implied but identical to the top equation?
They are supposed to be. You mean, is this equivalent to this?
No, the theta over, I guess theta equals to 3x bar versus theta hat equals to 3x bar.
Yeah, yes, you just do algebra, basically. Well, you do calculus at this point. But anyway, you just step through it, okay? Okay, so that's the method of moments. If I have more than one parameter, I probably have to go to k equals 2 as well. End of the day, I may find that this expression over here for the expected value will have both parameters in it. It'll have my theta 1, my theta 2. For instance, in the normal case, I might have both the mean and the variance as part of this expression. I do k equals 2, same thing. I might have both the mean and the variance. End of the day, then, I have two coupled equations, and I need to solve them, just as I would any set of two equations that have two unknowns in them. Okay, so that's just standard algebra at that point. And if we were so unfortunate as to have a distribution that had three parameters, we'd probably have to do k equals 3 and then solve three simultaneous equations, and don't worry, we won't do that. Okay. Yes?
Just to double check, when you go to the expected value of x squared,
Yep.
it just becomes the integral of x squared times x.
You bet. This is our generic expression for expected values. So, you know, I could put k's here if that makes you easier. The expected value of whatever is in here goes here. I multiply that by the probability distribution function. So, box. Okay.
One last question. If that expression is equal to the x bar for k equals 1, what's it equal to for k equals 2? Is it, it's not x bar squared, right?
Over here.
Yeah.
And then this wouldn't be true. Right? It's only the fact,
Yeah.
so this is what I write. This is the expression I use. And, you know, hey, what do you know? If x is equal to 1, then I call that x bar.
Okay.
But if I were to put a 2 here, that would not be equal to. Okay. Okay. Let me make some space, and we'll go on and do the maximum likelihood. Okay. So the next one says, or C says, show that theta hat equals 3x bar is an unbiased estimator. Okay. So, what is bias? Bias is my estimator is not going to give me back the correct parameter. So if I know the parameter, I can do this calculation. And in this case, what I'm going to say is that the expected value then of my estimator is equal to the expected value of 3x bar. We know that we can take the constant out for expected values, so that's 3 times the expected value of x bar. And from the part we did earlier, this gives us 3 times theta over 3, which is just theta. So the idea here again is we want to compare the expected value for our estimator to the true value. If they're equal, the bias, which is the difference between those, equals 0, then we have an unbiased estimator. If a problem asks you for the bias, you just plug it into this thing to give you the value. Okay. Okay. Now the interesting part, or the confusing part, depending on your point of view. Part D, which is find the maximum likelihood estimator for theta. Okay. So let's take a minute and go over maximum likelihood estimators before we solve for this one in particular. Let's see, we want to do that. I'll do it here. So maximum likelihood is based around this idea that what we know is two things. One, we know the PDF, f of x, and that it has some parameters in it. So if this is the binomial distribution, there's one parameter, it's the probability. If it's a normal distribution, there's two parameters, the mean and the variance. The other thing we know is our bunch of samples, x1, x2, and so on, up to xn. So we're going to make the assumption that, assume that all of our sample here is the most likely, well, that's not the way to say it. It's the, let's try again. So we're going to find our thetas, so the probability of our xi's is the maximum. So if I have a sample distribution that looks like this, I'm basically going to say, I'm going to fit my normal distribution to this so that the center is about like so, and the standard deviation is about like so that it looks like that's the most likely outcome in this case. So that's conceptually what happens. Mechanically, it's a little more complicated. So we create this likelihood function, which we say is a function of our parameters. It's really the joint probability distribution of getting these particular values, x1, x2, and so on. So this says it's my PDF for that particular x1. I'll put the theta in there because I don't know it. It's a variable as well. And then I've got a second sample, and I just multiply the probability of getting this sample times the probability of getting the next one. And I multiply so on until I get to the nth sample. Now, it's a function of theta, so I can now say, let me take a derivative of this to find the joint probabilities maximum. So the partial derivative then of L with respect to one of my theta j's equals 0 will give me the maximum probability. Okay. And the messy thing is I've got a big product here, so this is, calculus product derivative product rule from hell, because I'm going to have one term for each one of my n's. So we can get around that by converting our product into a sum using the natural log function. So I take the natural log of my L of theta, and that will just give me the natural log of each of these as a summation. And then I take the derivative of this, partial derivative of the natural log of n, set that equal to 0, and now I can find my thetas. Okay, so let's go and do that for our particular function here. But before we do that, let's look at maximum likelihood for the uniform distribution. Because this is really the key to understanding this part of the problem. So suppose I have the uniform distribution between 0 and some parameter a, and so this is 0, it's less than x, it's less than a. And the value here, of course, for the probability density function has to be 1 over a, so that when I multiply these, when I integrate, I get back 1. Okay. And now I got a bunch of samples. So each one of these marks you can imagine is a sample as I go along here. And they're uniform, so they're scattered everywhere between 0 and a. And now based on those, I want to estimate the parameter a. It's the only parameter in this function. And in fact, my probability density function is just 1 over a. Okay? So it doesn't even include anything else, just a constant value there. Okay? Well, now let's calculate our likelihood function. Our likelihood, and theta is equal to a in this case. So this is the probability of x1 and a, probability of x2 and a, and so on. Well, this probability is 1 over a. And this probability is 1 over a. Okay? So I'm going to have n of those, so this is just 1 over a to the nth power. Okay. Now, let's go ahead and do our natural log. And in fact, we can just think about the derivative of this directly. Let's just look at d by dA of L. It's not even a partial derivative because there's only one variable here. So this is d by dA of a to the minus n, which is minus n over a to the n plus 1. Okay? So the derivative of this, we want to find where it's equal to 0. There's a problem here. Okay, so for a lot of continuous functions, sure, I can take the derivative and set it equal to 0. What does this function look like? Well, let's draw a plot. So here's a, and 1 over a to some power looks, well, 1 over a to some power looks like a hyperbola. And now we have it on the negative axis, and the n is just a scaling constant here. So this function is going to look something like this. Okay? So at no point is this equal to 0. This number is always less than 0. This expression is always less than 0. Okay? So I can't use the calculus-based maximum likelihood idea. I can't take the derivative, set it equal to 0. But I can still find the maximum likelihood. Okay? I can still find the point at which the probability is the highest. But to do this, I'm going to go back to looking at the probability likelihood function. So here is L of a, and in this case, it's just 1 over a to the n, and again, that's this hyperbolic function here. So 1 over a to the n. And I'm trying to figure out what's the highest value for this. Now I've got all my samples here. I've got x1, up to xn, supposing they're ordered here. From those, what can I say about A? Well, one thing is clear. I can't have a value for A that is less than any one of these samples, because this came from that interval, 0 to A. I don't know where A is. It could be right here, or it could be out here. Not very likely to be out here, given that I've got a distribution in here. So my best guess for this is something like x max. the largest value for one of the samples that I took. So what does that look like here on my A scale? I've got some value that's x max, and so I know that the likelihood is actually 0. Let me turn that into a dotted line. And in fact, the likelihood function looks like 0 until it gets here, then it jumps up to this value and goes down. So what's the highest value for the likelihood function? This value right here. The maximum value for the likelihood occurs at the largest sample value. So you could go through and, oh, so now let's go back to our problem here. So recall that our function here is f of x is equal to 1/2 1 plus theta x, and x is between 1 and minus 1. What does that function look like if we were to draw it on a plot? Always good to draw pictures of these things. So here is x, and the domain is +1 to -1. And if we're going to draw this, let's note that this is 1/2 plus theta over 2 times x. Well, that is clearly the equation of a line where theta over 2 is our slope and 1/2 is the intercept. Okay. So if I do the quick little table, x and y, suppose I put in x is equal to 0, then this will just be 1/2. And if I put in x is equal to 1, the positive limit here, then this is going to be 1/2 plus theta over 2. And the other side is going to be 1/2 minus theta over 2. So if I pick, for instance, theta equals 0, then it's a uniform function with a uniform distribution of value 1/2. So this is the case, theta equals 0. Well, that looks a lot like this function we just did right here. Okay. What about if I put in theta equals 1, and then this is 1/2 plus 1/2, that'd be 1. This is 1/2 minus 1/2, that's 0. So this is a line like so, theta equals 1. And since theta over 2 is the slope, I'm just going to get numbers that pass through my intercept at 1/2 here at different angles. Okay. So really what this problem was about was looking at cases where we have, instead of a uniform distribution, we have a distribution with some slope over a finite interval, once again. Okay. So let's look at how we would do the maximum likelihood function. So we know that we could go through and calculate our partial derivatives, but from what we learned here, I think it's immediately clear that our likelihood function is going to come out looking something like this, and the maximum value is just going to be, again, equal to x max. So you can just write directly from analogy with the uniform case, the maximum likelihood estimator, of A is equal to x max in this case. Okay. Okay, so that problem, again, was designed to get you to think about what maximum likelihood means rather than just the turning the crank, taking the partial derivatives along the way. This uniform example, by the way, is in the textbook, so that is worked out in detail for you in the textbook. Yeah.
I'm a little bit unclear about the graph that you got over here for the maximum likelihood.
Yep.
It's 0 until you get to x max.
Yeah.
Why is that?
Okay, this is clearly true that the maximum likelihood, what does maximum likelihood mean? It's the value of the parameter which maximizes the likelihood for all the data points that you have. So you're going to pick your values so that it's likely you'd get the data you got. Okay. Well, the data you got is spread across this interval, but we know that this one's near this end. Okay, so what's the likelihood that it's less than the value you know it's bigger than? It's 0. Okay. It's not a numerical computation. If you're looking for a numerical computation here, that's not what this is about. This is conceptual. This is thinking about what does maximum likelihood mean. Okay. And in this case, it means I'm going to pick my estimate of A so that it's maximum likelihood, and in this case, I know it's 0. It's got to be 0 for everything less than that. Okay, so let me move on then to the next part, the confidence intervals and so on. Go. Okay, so chapter 8. We went through a lot of special cases there, but the basic idea is the same. I have a distribution. I'm estimating for the mean, the population mean, where I've got a distribution like so, the population mean in the middle, and I say that as I draw samples, I'll get different values. But gee, if my samples are way out on the edge, I'm going to discount it. I'm going to say it's so unlikely. So if, for instance, I have a tail like so, then I'll want to say what the likelihood of the mean being within this range that I'm looking for would be. So what is this distribution? It's the sampling distribution for the sample mean. Okay. So let's do the following exercise. I've got a population. This thing's failing. Let me see if I can get a better one. Oh, much better. Okay. How would I describe the population? Well, if it's normal at least, I have a mean and a standard deviation. So I've got a sample. Oh, I can calculate the sample mean, the sample standard deviation, and of course I know the number of samples I took. Bar, S, and N. And now let us construct a tree diagram for how I would calculate a sample interval, or a confidence interval, depending on what I know along the way. Okay, so my goal is to do a confidence interval. In one direction, I'm going to use the z distribution, And in the other direction, I'm going to use the t distribution. And that's the real challenge in a lot of this is I ask you to do a confidence interval, and you got to decide which formula do I use. Okay. So let's try to figure out how to do this sort as to which one I'm going to use. What are some of the reasons I would use z and not t?
You know variance, population variance.
If I know my sigma, okay, is that alone enough? If I know the population variance or standard deviation, do I always use z? Yeah.
Does the population also have to be normal?
Or
That's it. Okay. You know sigma, and either of two things is true. It's normal, or n is big, whatever big means, greater than or equal to 30, greater than or equal to 50, depending on what you like. What else might I use one or the other?
So population is normal or with large sample?
Yes, it's either the population is normal and I know sigma, or, let's try that again, either doesn't belong there. Either both of those things are true, it's known sigma, no, that's not, I got that wrong again. Let me try this again. Okay, so what are the cases? If n is greater than or equal to about 30, I'm good with C. Doesn't really matter what the population distribution is, right? Okay. What if it's known to be normal, and that's not true? Then what else has to be true for me to use Z? Yeah. So I have to know my population standard deviation or variance. Okay. Okay, what about T? What are the conditions I'm using T? Has to be normal. Okay. Do I need to know the standard deviation?
Sample standard deviation.
I'm sorry?
You need to know the sample standard.
The sample standard deviation, yeah. So in this case, I use S. In this case, I use sigma here or S here. Let me just indicate that. I hate lines. So for here, I use S. For here, I use sigma. And here, I use S again. Okay, what's the formula I use in this case? In this one, it's x bar plus or minus z of alpha, s, or I'll write sigma over the square root of n. In this case, I write the same thing, x bar plus or minus t alpha, and I also need n minus 1, the number of degrees of freedom, times s over the square root of n. Same formula, you just have to think about which z or t.
Shouldn't that be alpha over 2?
Well, would it be?
When you're doing two-sided, divide plus and minus.
If it's two-sided,
Plus and minus, I guess.
you're right. If I wrote it as plus or, no, it's still a confidence interval in this case. So yeah, you could, depending, if it's two-sided, you write over 2. Otherwise, use alpha. Okay. Let's now talk about hypothesis testing. what's the idea here? Why would I bother with a hypothesis test if I can use basically the same formula to a confidence interval? Yes?
If the population is non-normal and you have a small sample size,
Pray? Consult an expert?
so that wouldn't be a case that's inclusive versus constant.
Correct. We talked about that a little. There are two ways you can go. One way is you can actually calculate what the statistics would be. Okay, so analytically it's possible to do that. There are formulas. If you look in advanced statistics texts or you talk to a statistician, they can tell you, oh, for binomial, here's the test you would use, for instance, for small n, small p or something. Alternatively, you can use a computer to calculate numerically what the sampling distribution looks like, and then use that to do your confidence interval calculation. That, you won't be asked to do any problems like that. Okay, why would I use a hypothesis test when I have a perfectly good confidence interval? Good question. Okay, and the answer is we're able to do stronger kinds of tests. We have type 2 and, or type 1 and type 2 error analysis. And type 2 errors in particular help us to find sample sizes that allow us to avoid making mistakes. So the type 1 stuff, that's really all about confidence intervals. It's really the same thing as a confidence interval. Type 2 is where we figure out if we're going to make another kind of error. So let's draw this little diagram again. Well, no, I have to start with hypotheses before I go there, don't I? Okay. So we make two hypotheses. We start out with a null hypothesis, H0, which says that the mean of our population is equal to some value, 0. And then we have an alternative hypothesis. I'm sorry, it's not equal to 0. It's equal to mu sub 0. We have an alternative hypothesis that says that the mean is greater than, less than, or not equal to that value. Okay, now there are two kinds of errors we want to worry about. Now we'll do the table. Okay, so in one case we'll reject H0, and H0 is true. And we might not reject H0, but H0 is false. Okay. So what do I write in each one of these squares? Okay, suppose H0 is true, but I reject it. That's an error. What kind of an error is that? Type 1. Okay. And what's the probability associated with getting that kind of an error? That's our alpha. Same as over here, where we're out in the tails. We're saying, what's the likelihood I got a sample as far from my hypothesis as that? Now, of course, if H0 is true and I don't reject it, life is good. If I reject H0 and it's false, life is good. But down here, I don't reject it, even though it's false. That's the type 2 error. And the probability of that we call beta. So once again, we have all these different flavors. Which particular test we use for our test statistic depends on the same kind of things we saw over there. So Z versus T, same kind of ideas. If I have a known standard deviation and it's normal, or if n is big, I use t if it's normal and n is small. Now and this is for my alpha type 1 errors. And for the type 2 errors, we derive formulas to find our z of beta, and that's going to be a function of our z of alpha, and also of the number of samples we take. And we can flip that over, and we found formulas for n that are a function of z alpha and z beta. Okay. And we use different formulas depending on which one of these situations we're in. Okay. Okay. So that's all the material I had prepared. I'm happy to answer questions or go over homework problems or whatever would help. Yeah.
I don't know if you remember this off the top of your head, but there are subsections of each chapter that say we don't have to study. Do you remember which ones?
I can go through them, yeah. It's on the website too, I believe, in terms of the readings. I mean, the real key is the problems to look at there. Yeah.
One thing that we didn't talk about today, but we went over a lot in the section was tolerance intervals.
I'm sorry, was?
Tolerance intervals?
Tolerance intervals. We're not covering those this year.
Oh, okay.
Yeah, tolerance and prediction intervals we're not going to cover.
Okay.
Jen?
Test of goodness and bad.
Nope, didn't do that either. Yeah, so that stuff is in, is that chapter 8, I think, where we didn't do 8.6. Let me find a place to write this. Chapter 8.6, tolerance and prediction. And chapter 9, goodness of fit, 9.7. Goodness. Okay. Or, 9.8, 9.9. Other questions? Yeah.
Can I ask a question referring back to the maximum method?
Yeah, you bet.
So the f of x function was 1 over a in the unit context, right? And you're assuming, I guess a given set of data or a sample for x1 through xn. And I guess the result that we got was that the best estimation for a is max of the data set x1 through xn. Isn't that technically minimized rather than maximized?
Yeah, because of the shape of the function, I can see where you're getting that. Let me see if I can address that more directly. Okay, so. Okay, 1 over a to the n, here's our a-axis. And the idea is we've got some x max, and we know that the maximum likelihood function, L of a, looks like this. It's 0 until it gets to this guy, and then it pops up here. And if we can minimize, because I'm actually sliding down this, You're saying I'm minimizing it?
What I'm saying is that L of A is 1 over AN, but just going back to, I guess, as you mentioned, the intuition behind maximum likelihood estimation, you want to choose a value of A such that f of x, the original distribution function, is maximized. In that case, because f of x is 1 over A, wouldn't you want to then choose min of xi rather than max of xi to maximize?
Okay, yeah, so, yes, if you just plug the values of xi in there, you would get a smaller value for the likelihood, but you want to maximize the likelihood. So the key point is that the likelihood is 0 for any of these values less than xa. So if I plugged in a smaller value, I'd be plugging in a 0 likelihood. Again, if you go back to the distribution function, the PDF, f of x, we know that between 0 and a, I have equal likelihood. So all my x's are in here. And a cannot be less than x1, right? The probability, the likelihood would be 0 that this number is on the other side here. I cannot have a sample over here. Okay, 0 probability.
So I guess what I was trying to say is that as long as you make the interval from 0 a smaller, then the height of that function is going to increase. So then the individual xi's will have a higher probability and they'll be maximized, I guess, as a approaches 0.
I think I agree with you from what I heard. Was that a statement or a question?
It's a statement then that wouldn't that imply then a should be estimated by x min.
Okay, but if it is x min and it's down here, so now my probability density function looks like this or whatever,
Right.
how do I explain that I got data samples that are greater than the interval? It's not possible. Yeah. Right, that violates my assumptions about the sample space. Jen?
I was just curious, when will we know we can use that? Like, just if the PDF is a little bit linear, then we know that it's similar to uniform?
Yeah, so where I would like you to get is, rather than turning the crank, so we all want to turn the crank, right? We don't want to think, we want a formula. So you put the problem in the top, you apply the algorithm, and out pops the answer. But it doesn't always work. Even in the simplest probability distribution uniform, the maximum likelihood algorithm, where you take the partial derivatives, you take the log, doesn't work. But the idea works. So if you go back and say, gee, what I'm trying to do is maximize likelihood, then this makes sense, then you can come up with the right answer. So the maximum likelihood idea should be in your repertoire. You need to know how to do the log partial derivative trick, and that often works for continuous distributions, but it doesn't always work, and if it doesn't always work, you should be able to come back to thinking about, gee, how can I maximize the likelihood of this function, even if I can't take the derivative, even if the calculus-based approach doesn't work. That's the goal.
So when you take the derivative of the function, and you get something like you had, where it was like 1 over a to the n equals 0. So there was, or negative n over a to the n. So there is no way that anything in that, like it's just 0 because you set it equal to 0. There's no plus or minus in there. There's only multiplication and division.
I'm sorry, I didn't get the argument there.
So when you take the derivative of the function,
Yep.
and you wind up with something that like you had negative n over a to the n.
Yep,
So
and you
that's
set that equal to
only
0.
Division and exponents, and you set that equal to 0, there's nothing you can get besides 0. Is that always an indication that something like this is going to happen? Like it's not going to cross 0?
Yeah. Let's see, so you can come up with an expression. In fact, with this problem, if you put it through, you come up with an expression at the other side that I don't know how to solve. Okay, so grinding through, you may get to the point where you get an expression, it's not clear that it's not solvable, but at the end of the day, you may have to step back and say, I don't know how to solve it, there doesn't seem to be a way to solve this, so can I go back and say, is another way to think about this problem and apply the concept of maximizing likelihood that'll tell me what the right answer is, and not have to solve a crazy expression I don't understand.
Can we pick up old P sets?
Yes.
Where are they?
Where are they? Melissa brought them in, I thought. She said she was going to bring them in. Are they on a table here? Okay, she didn't bring them. They're either in her office or my office. I'm happy to walk down there right after this and grab them for people. But she said she was going to bring them, so I'm kind of surprised they're not lying around here. Okay, anyway. We all got so excited about the camera, I think we lost track.
Is it, I guess, okay to think in terms of the maximum likelihood if we have a 1 over a to the n, say that for that to be equal to 0, like theoretically, the denominator should be infinity, therefore the largest number that we can get from our sample.
I missed the infinity part.
So I suppose 1 over a to the n will be 0 as
Oh, yeah. Mm-hmm.
a over n goes to infinity.
Yep. Mm-hmm.
But the largest, I suppose like the closest that we can get to infinity would be the maximum.
Oh, that's an interesting way to
maximum-
phrase it.
Like the
Yeah,
maximum,
yeah, yeah.
like
And that's
sample
what I was
size.
thinking originally. I still don't understand why it's equal to 0 but at less than x max. Is that clear to people? Or like, am I here? All right.
Because
I could ask at another time.
People
Because
want-
logically, it doesn't make sense for it not to be equal to 0.
Because if A is like less, if you have values, sample values greater than A.
Suppose I were to say it's like this, okay? I'm gonna pick this x, that's my estimate. X3 is my estimate. Well, then how do I account for the fact that I got a number larger than this? If I have a number outside the distribution, I define my distribution, to 1 over a, and then I somehow get a sample that's outside my distribution, how can that be? It violates the assumption of what the sample space can be. So, yeah.
Just as a logistic question, I know in the problems that I think the last one, the definition of alpha might be different depending on the textbook and who's writing the question. On the table that's going to be given for the exam, would it say which alpha it's, I guess?
Okay, so two answers to that. The first is the difference between a CDF table and a percentage point table. And the second is sort of the level of comprehension you should have, okay? So the first one, do people get the difference between the Z table and the T table and the chi-squared table, what the difference between those are? Okay. So in the one case, you get the, let's see, for the Z, let's draw it, because I'll get right and left mixed up. So for Z, if I have a particular value of Z here, I get the area to the left of it, okay? If I have a T table, it tells me what the value of T is for that particular distribution upwind, on the right side. So let's see, so for this table, the rows and the columns give you the integral, the CDF. In this case, you get the CDF and it gives you the T value. The row in the column is Z, and that gives you the value of the integral. In this case, the row in the column, well, the row gives you the percentage, the alpha, no, that's backwards. The column gives you the alpha, and the row gives you the number of degrees of freedom, and then based on that, you read your T value off that. And in this case, it's, the area below, and in this case, it's the area above, okay? So I think that may be the difference you're referring to when you say which alpha is it?
Well, on the last problem there, I think the last question, it was saying.
You said alpha of 90.95.
instead of 0.5.
Right, 0.05.
Yeah. Right, so hopefully you would know, I think it's reasonable to expect that you would understand what that means. So some people refer to it as a 95% confidence level, some people refer to it as a 5% confidence level. Would it make sense to ask for a, 95% of the curve tail? It would always be, you're always worried about when it's unlikely. How unlikely is this sample? Well, if it's 95%, then the sample's going to happen. There's no inference to be done. So I think it should be clear. You're always interested in going out into the tails. Okay. Other questions? And I'm happy to stick around and answer individual questions afterwards as well. But first, I'll go down and get the problem sets, which I hope are not lost.